Welcome back, calculus students. This is part 2 of the video notes for approximating areas, where we're actually going to get into approximating areas. So what you have here is a curve with a shaded area underneath it labeled A, and this curve is bounded by the function f of x, the x-axis, and x equals a, x equals b. So there are 4 boundary functions constricting this area. Now, a partition is just any division within this area. And a regular partition is when those partitions are equally spaced. So with regular partitions, we're going to be calling this distance here delta x, representing the change in x. And then the height of the function at the end of the partition is f of x. So as we get into the notation, you're going to see something like delta xi, or just xi, and you're also going to see f of xi. And these are basically referring to each of the rectangles you choose to divide your function into. So this example here, I've divided it into n equals 4 partitions because we have 4 rectangles. So the first thing we want to get into are left and right endpoint approximations, and these images just come from your textbook. These are called left endpoint partitions, and with this increasing function, you can see that we're going to be getting an underestimate for the area since each rectangle lies below the function curve. And so it starts at x0 and it ends at xn minus 1, where this would be n right here, xn right here. On the flip side, your right endpoints don't start at x0 and they end at xn. And so there's slight differences in the formula. F of xi, meaning you'll end at xn when you're done, and f of xi minus 1, which means you will start at x0. So like this would be x1, this would be x1. And so your area is approximately the height of the function at your x point times delta x, which is the width of the function. And this is just your basic area of a rectangle, length times width, or height times width, however you want to think about it. So we're going to try this out using both left endpoint and right endpoint approximations to approximate the area under the curve of f of x equals x squared on the interval 0 to 2. So I'm going to start with a picture. And by using colors, I'm going to attempt to get away with doing both approximations on the same image. So here's 1, 2, 0. And with f of x equals x squared, I know that it starts at 0 and that we have 3, 4, 1, 1, as well as 2, 4. So we're going to have some curvature like so. And it's asking me for 4 partitions. So I'm going to switch to kind of a gray color here. If I draw this vertical line here, that is 2 partitions, 1 and 2. So I'm going to need to draw one here and here to get 4 partitions. Now let's start with our left-hand approximation. So a left-hand approximation starts at 0. And at 0, the height of the rectangle in this example is just 0. So for my first sum, I want to do f of x times delta x. Well, f of x is 0, that's your y value. What's delta x with this number of divisions? Well, we've got 0.5, 1, 1.5, and 2. So delta x is 0.5. Plus, and we're going to say L4 is equal to. So our next left-hand endpoint is 0.5, and we need to know this exact point right here. So what do you get when you do 0.5 squared? You should get 0.25. So the height of the function is 0.25, and the width is still 0.5. For our next one, we're talking about the left endpoint being at, let me draw that rectangle, 1, and we know that 1 squared is 1, so the height of the rectangle is 1, and the width is 0.25. Finally, our fourth rectangle does not start at the boundary of 2 because this is a left-hand sum. It's actually going to start at 1.5, the last partition, delta x away from the end boundary. So what is 1.5 squared? We should get 2.25 for our y value. So we're going to do 2.25 times 0.25. And that's going to represent our left-hand approximation for x squared, for the area under x squared from 0 to 2. Based on this picture, you guys can tell that this is a left-hand approximation. Sorry, I'm just fixing. I started putting 0.25 instead of putting 0.5. This is an underestimate, this left-hand approximation, because each rectangle I drew was underneath the curve. All right, on the other side, we're going to be doing the right-hand approximation. I tend to still start on the left, even though I'm doing the right hand. The only difference is I'm not starting at 0. I'm starting at 0.5. And the height at 0.5 is 0.25. And the width is 0.5. So we've seen this term before with our left-hand approximation. And the rectangle looks like this. It actually goes above the function. Then we have our point at 1, which goes up to 1. So we're going to have a height of 1 and a width of 0.5. Again, that term is shared in common. 1.5 goes up to 2.25, the last common rectangle. And finally, our end, which is our right end point, goes all the way up to 4. And so we're going to get 4 times 0.5. Using a calculator, evaluate each sum, and let's compare the difference. The true area should be less than the right endpoint and greater than the left endpoint. So we're going to do 0.25 times 0.5 plus 1 times 0.5 plus 2.25 times 0.5. I did skip the 0 because it's going to equal 0. So we get 1.75 for our left-hand approximation. And then for our right-hand approximation, we're going to repeat these. Sorry. And then add in the last rectangle. And we get 3.75. And so we know that the true area under this curve is something in between 1.75 and 3.75. Okay, so then we're going to talk about how this leads into the types of sums we want to be calculating, which are ultimately going to be called Riemann sums. And this idea is that the more partitions you have underneath your curve, the better your accuracy will be. So here we have 4 partitions with a left-hand and a right-hand sum, and our areas are 7.5 and 8.5 respectively. You can see quite a bit of overlap or underlap in the area calculation. When we double our partitions, we're minimizing the gaps. So now our areas are 7.75 and 8.25. And then if we quadruple it to 32, you can see that this area gap is really small at this point, and our areas became 7.94 and 8.06. So you can see that we're approaching a limit of the true area, which in this example is actually exactly 8. And so we want to take our areas as limits as the number of partitions goes to infinity. So here's our Riemann sum. We've got our height of the function at the partition that we care about. It's an asterisk because it can be a left hand or a right hand. And then delta x is the width of your interval, and n is the number of your partitions. If f of x is a continuous non-negative function on the closed interval, then the area under the curve is just the limit of the Riemann sum as the number of partitions approaches infinity. So let's take a look at lower and upper sums. Find a lower sum for f of x equals 10 minus x squared on 1 to 2 with n equals 4 subintervals. First, we need to draw this negative quadratic from 1 to 2. So here's 0, 1, and 2. If I plug in 1, I'm going to have this go all the way up to 10, just because I know that that's the maximum. So we're going to go 1, 2, 3, 4, 6, 7, 8, 9. When we plug in 1, we get 9. So we've got our point 1, 9 here. When we plug in 2, we get 6. We've got our point 2, 6, and then try to make it kind of look curvy. It's not going to be very curvy. So here's the area we're trying to approximate. If we have 4 intervals, there's 1, 2, 3, then we know that each interval has to be 0.25 to accommodate the distance 1 to 2. So you can always calculate your delta x like this, which is b minus a divided by n. And so in this case, our delta x is 0.25. And so on this one, if we wanted to do a lower sum, notice I'm no longer saying left hand and right hand. If we want to do a lower sum, we need all of our rectangles to be below the curve, like this. And so it turns out in this example that the lower sum is actually the right-hand sum for the function. And so our lower sum is an R4. And for the first point, man, we're going to use a table for this because it'll get a little ugly. And we're also going to do a little shortcut. So let me take you back to one of our other sums. Do you notice how there's a 0.5 factor on each term? That means that that 0.5 can really just be calculated once. In this case, it's a 0.25. And so all we need are each of the y values at each of the right endpoints. So I'm going to build a table with our function, which is 10 minus x squared. Oh, hold on. That did not come out nice. Minus x squared. Clear that out. And then for my table settings, I'm going to start at 1, and I'm going to count by 0.25, which is our delta x. And then table. So this is just an easier way to get my values, which now I know at 1 it's 9, I already knew that. At 1.25 it's 8.4375, at 1.5 it's 7.75, at 1.75 it's 6.9375, and at 2, which I knew, it's at 6. So this just makes it a little bit easier to get those values to calculate this sum. So the first point we care about is 1.25, so we're going to do, I wonder if I can fraction this. I feel like that'll be a little easier to write. Math. Okay, so I'd rather fraction it, but it won't let me. Maybe if I do table settings, delta table, and switch it to 1/4. Let's try that. Sometimes you can trigger the calculator to evaluate in fractions. Beautiful. Well, that's not easier to write. Okay, so 1.25, we've got 135 over 16. Yeah, good investigation, not worth our time. So we're going to do 0.25 again and just, oops, bite the bullet and write out all those decimals. 0.25, table. Okay, so we've got 8.4375 plus the next point, which is 7.75, and I've got 4 partitions, so I know I'm going to need 4 of these. And then we've got 6.9375. And our last point, which is not going to fit, just kidding, it's 6. Go ahead and add up that sum. And our lower sum, which ended up being a right-hand sum, approximates the area as an underestimate of, I can see both at the same time. A little scroll. 8.4375 plus 7.75. I don't know why it keeps deleting on me. 0.25, 0.4375. .31 or so. Okay, similar question. For this last example, we're going to be finding an upper sum for f of x equals sine x over the interval 0 to 2 pi. Let's get a graph going of 0, and it would benefit you, I think I said 2 pi when I should have said pi halves, to maybe take a peek at a unit circle, although 6 subdivisions on a pi half scale is going to take us off our unit circle, so that's up to you. Sine does go positive and negative, but from 0 to pi halves, we're in quadrant 1, and that entire time, sine is actually going to be positive. So half of pi halves is pi fourths, and then 6 subdivisions actually means I need to cut this in thirds, and I need to cut this in thirds as well. And so we're going to go from our smallest interval, which will be pi twelfths, and then we've got pi sixths, and then we have pi fourths, should have pi thirds, and finally we should have 5 pi twelfths if we're just adding 1/12 each time for each interval. This can go up all the way to 1, maybe we record 0.5, and so we know that sine typically starts at 0, 0, and then by pi halves, sine is equal to 1. And you might also know from studying the unit circle at pi 6, it's at 0.5. And it's okay to use a rounded value here. I'm going to use that trick where I just make a table and allow my table delta to change by my delta x. And so my delta x in this case is pi twelfths. So that's also what I'm going to make my table settings count by. It might even be to my benefit to do this problem completely in expressions, exact expressions, and then calculate the sum all at once. The only thing I need to pay attention to is what an upper sum is going to look like. So let's take a look at what 5 pi twelfths. Let's just say twelfths. And let's just connect these. So if we're doing a left hand, an upper sum, that means we're looking for an overestimate of this function. And in this case, we're going to need a right-hand sum to perform an overestimate. So if you take a look at my first rectangle here, carry this up to the right end, there's an upper sum, and carry it down. That's what our 6 rectangles are each going to look like. So from the function, overestimate, like so, and then here, and then this last one here. So for this, I'm going to leave everything in terms of the trigonometry. So I'm going to say my upper sum with 6 subdivisions is going to be my delta x, which is pi twelfths, times each of these right-hand points. So my first one is sine pi twelfths, and then I've got plus sine pi sixths, plus sine pi fourths. And to reduce rounding error, I'm just going to type this in all at once and round my final answer. Sine of pi thirds, sine of 5 pi twelfths, and, oh, close parenthesis too soon, sine of pi halves. Okay, type this in all at once. Make sure you're in radians mode and not degree mode. And so I usually switch a lot because I teach calculus and trigonometry, but I think we've been pretty much radians mode for most of this class. So your settings might already be set to radians plus sine pi fourths plus sine pi thirds plus 5 pi 12ths. I'm really curious what a Casio, which can express trig functions in exact terms, it would make of this answer. And so I'm getting about 1.125 for my overestimate of the area beneath this curve. And that concludes the video notes for this lesson on approximating areas and Riemann sums. We'll continue to use Riemann sums in the next lesson on the definite integral before learning the fundamental theorem of calculus, which gives us a really nice algebraic shortcut to evaluating a definite integral.